Hello, my name is Prisha, and today we're going to be talking about GCD and LCM. What will you learn about today? First, we'll talk about the definitions of GCD and LCM. Then we'll learn 3 strategies to calculate both of them. Then we'll do a couple of examples to test our skills, and finally, we'll do a challenging question to really see if we can apply our skills in multiple contexts, as will be tested for on the ACT or other big tests. Okay, so first of all, what is GCD and what is LCM? Let's start with the GCD. It's essentially the largest possible integer that each number in the set is divisible by. So let's take, for example, the GCD of 9 and 15. Since the acronym GCD has the word denominator in it, I like to visualize the word like a fraction. So the GCD would be the number that goes in both of these spots, the denominator of both fractions, so where this x is. That makes each fraction simplify to a whole number. Next, LCM. LCM is the smallest possible integer that is divisible by each number in the set. So I'll use the same numbers 9 and 15. And I like to think about it in the same fractional sense, but as the numerator instead of the denominator. So it would essentially be the number that goes in the numerator, both of these fractions, where the x is, that causes each fraction to simplify to a whole number. But how do we calculate GCD and LCM? Well, the first method that we can use is called factors and multiples, and it's the best method to use when the numbers seem relatively simple, as in those numbers are easily divisible by numbers you know, or those numbers are easily multipliable, like in the 1 to 12 range, since those are your timetables. For GCD, you'll want to compare all the factors of the first number and then compare it to all the factors of the second number, and the biggest number in both sets will be your answer. For LCM, you'll want to find multiples of both numbers until you find the first number that's common to both. So let's find the LCM and GCD of 9 and 15. And let's start with the GCD. So for GCD, we want to find all factors. So I'm going to write down all the factors of 9 and 15 right here. So for 9, 1's a factor, 3 is a factor, and 9's a factor. For 15, 1's a factor, 3's a factor, 5 is a factor, and 15 is a factor. And we'd want to find the biggest number that's in both of these sets. Since I think 3 is the only number common in both of these sets, I'll do like a circle to show. The GCD of 9 and 15 would be 3. Okay, now on to LCM. We're going to find multiples of both numbers until we find the first multiple common to both. Okay, so for 9, we'll start off with 9, and for 15, we'll start off with 15. So first, let's multiply 9 by 2, we'll get 18. Let's add another 9, we'll get 27. Let's add another 9, and we'll get 36. Let's add another 9 and we'll get 45. I'm going to stop here because I'm running out of room. We'll see if we need more. So for 15, we're going to add 15 and we're going to get 30. And I'm going to add another 15 and we're going to get 45. So now I see we have 45 in both of our sets, which means that our LCM would be 45. As you can see, since both numbers are relatively small, this was a pretty easy process. But obviously, if you get very big numbers or numbers that aren't as easily divisible as this, you're not going to have as great of a time trying to use this method. So that's why we can move on to the next method, which would be the prime factorization method. It's a bit time-consuming if you're not familiar with how to do a factor tree, but it's relatively simple and straightforward if you do, so choose wisely. That being said, it's not hard to do a factor tree, and we'll be going over how to do a factor tree with this method. So don't worry if you're not in the headspace to do a factor tree. So again, we're going to do the GCD and LCM of 9 and 15. For GCD, we'd want to multiply the smallest powers of each prime from both factorizations. And for LCM, we'd want to multiply the highest powers of each prime from both factorizations. If this doesn't make sense, don't worry, I'm going to explain it. When we work it out, it'll make a lot more sense. So let's start with the GCD of 9 and 15. So our factorization tree for 9, the smallest prime that goes into 9 is 3, and what's left is 3, which is a prime, which means that this is our factorization tree. For 15, the smallest prime that goes in here is 3, because it's not an even number, so 2 can't go in there. And what's left is 5. 5 is another prime, so that's our factorization tree for 15. Now, let's write it out in power format. So 9 would be 3 to the second, and 15 would be 3 times 5. Okay, and now we're going to multiply the smallest powers of each prime from both factorizations. So since we only have 2 primes, 3 and 5, we're going to multiply the smallest power of 3 that we can see times the smallest power of 5 that we can see. And the thing that's going to make this easier for us is if we write down missing primes. Since I see 9 only has a 3 squared in its factorization, I'm actually going to multiply it with 5 times the power to the power of 0, because we need another prime to match up with the prime here. But if we do 5 to the power of 0, which essentially means that there's 0 5s here, 5 to the power of 0 is 1, so 3 squared times 1 is still 9, and we're not changing this formula at all. It's just that we're adding this 5 to the power of 0 to kind of make it easier to visualize for us. So the smallest power of each prime. So the smallest power of 3 I see is 3, because 3 to the second would be the bigger power. And we'd want to multiply that by the smallest power of 5. We have 5 to the power 1 and 5 to the power 0. Since 5 to the power 0 is smaller, we're going to write that here. And since 5 to the power 0 is essentially equal to 1, this is going to give us 3. And as you can see, that's the same answer that we got last time, so we know that's correct. Now for LCM, we're going to multiply the highest power of each prime from both factorizations. So actually, this method is very good if you need to find both the GCD and LCM of two numbers, because once you do the work for GCD, it's very easy to calculate LCM, and vice versa. So the highest powers of each prime. So the highest power of 3 would be 3 to the second. Highest power of 5 would be 5. And we'll get 3 to the second times 5, which is 9 times 5, which is 45, which is exactly what we got last time, so we know it's correct. So this is a very reliable method, and it's a lot less time-consuming for bigger numbers because your factorization trees are never going to be super huge. They're always going to be somewhat manageable based off of the questions that they're going to offer you in exam. So this is arguably the better way to do it. You just need to get familiar with doing factorization trees. And the only thing you need to remember with factorization trees is pulling out the smallest prime, seeing what you're left with, and keep pulling out small primes until you're ending up with a small prime on the right side. So let's continue. Now method 3. If you're on the calculator active section, you can do this method too to get a fast, easy answer. Here are the steps, though unfortunately I can't demonstrate them right now. So first and again, this is on the TI-84, I'm not exactly sure how this would translate over to other calculators, but it's very easy to look this up online and check if you do have another calculator and you're interested in using this method on the calculator active part of the test. So on the TI-84, you're going to click the Math button. Then you're going to scroll right to Num by using the arrow keys. You're going to just click right. And then for GCD, you're going to press 9. That's going to bring you to the 9th choice. Then you're going to press the numbers in your set. So like 3 and 5, for example, or like 7 and 4. And then you're going to click Enter. And that's going to give you the GCD. And for LCM, you're going to press 8, do the numbers instead. press enter, and you're going to get the LCM. This is really useful in case you have really big numbers that you need to get GCD and LCM for. And if you're on the calculator active section and you don't want to waste extra time in doing factorization trees and finding GCD and LCM, this is a totally valid way to do it. Just don't get too reliant or dependent on it when you're solving calculator inactive questions, because obviously you're not going to be able to do that on actual tests. So let's go on to some examples to really hone in on our skills. So our first question is find the GCD and LCM of 100 and 270. And since these look like very easy numbers to divide and multiply, I think I'm going to use the factors and multiples method. So GCD, I'm going to see what the factors of each of these are. Okay, so 100, I'm going to write out 100 here. 100's factors are 1, 4, 25, 10, sorry I didn't put that earlier, and 100. 270's factors are 1, we can do 30 and 9, and also 3 and 90, and also 10 and 27, and there's a couple more combos, but I think I see already something that would work for 100 and 270, so I'm going to stop here. So I see that we have 10 here and 10 here, and since there's no other factor that I can see in both of these sets that would really match up, I think 100 would be our GCD. As you can see, this method is a little bit of like a guesswork strategy because sometimes you don't recall a couple of the multiples and then that can throw you, or a couple of the factors, and that can throw you completely off. So again, I only really recommend this for numbers that you're really sure of the factors and multiples, and you can catch them all. Next, the LCM. So I'm gonna take the short method here just because if I wanted to, I would write out 127 times, but for the sake of time, I'm not going to. But what I'm going to see about 270 is that we need to find something that that we can multiply 270 by to get 2 zeros on the end. That's the only way we're going to get something that's a multiple of 100. So the only thing that I think I can really multiply 270 by to get 2 zeros on the end would be 10, because that would essentially just add another 0 on the end, and that would give me my 2 zeros that I needed. If I wanted to multiply by 5, I would end up getting something that has 140 added to it, which wouldn't give me those 2 zeros on the end, which isn't what I want. So I'm going to say that my LCM would be 270 multiplied by 10, which would be 2700. Sorry, this is a bit messy, but yeah, LCM is 2700. Okay, our next example is what is the least positive integer divisible by 3, 7, and 14? So with these multiple choice questions, they're actually very easy with LCM and GCF, because what you can do is essentially a condensed form of trial and error, and it's much faster than actually trying to figure out like the least possible integer by multiplying things out and doing factor trees and such. So therefore, let's start with the smallest answer choice and work our way up to the largest. That's what we would do for LCM because if we started at a large answer choice, it could actually work. It could be divisible by 3, 7, and 14, but we wouldn't know if the smaller answer choices are divisible by 3, 7, and 14 too. So we'd want to start with the smallest and work our way up, so that way we can find the least positive integer that would be a multiple for all three. So let's start with 28. Is 28 divisible by 14? Yep. 28 divisible by 7? Yep. I'll start again. 28 is divisible by 14 because 28 divided by 2 is 14. 28 divided by 4 is 7. And 28 is not, 3 doesn't go into 28 because the closest number that would go in, that 3 would go into would be 27. So this doesn't really work. So I'm going to cross out E and we're going to go on to D. So does 14 go into 42? Yep, 3 times. Does 7 go into 42? Yep, 6 times. Does 3 go into 42? And I think it does. It would go in 16 times because, or sorry, not 16 times. We would have 14 times, sorry. So it would be 14 plus 14 plus 14. And actually, if you saw that 14 went into 42 and it would be 14 times 3 equals 42, it's obviously divisible by 3. So silly me, it would be D. And again, this makes it very easy to solve for things. Remember, you'd want to do the opposite for GCD. If it's asked for GCD, I'd want to start at the largest answer choice. Okay, last question. This one's the hard one. Read this question out yourself first and see if you can solve it while pausing your video. 3, 2, 1. Okay, are you done? Awesome. Let's get to solving. So the integer k is equal to m squared for some integer m. So k equals m squared. That means k has to be a perfect square, which means we're looking for a perfect square. If k is divisible by 6 and 40, okay, so what does this mean? If k is divisible by 6 and 40, that means the LCM of 6 and 40, the least common multiple, must be a factor of k, meaning that essentially the least number that this divides into has to be a number that k is composed of, because that's the only way that k can be divisible by 6 and 40. And we'd want to find the smallest possible positive value of k. Okay, so let's find the LCM of 6 and 40. That way we can figure out what the factor of k is. So 6, I'm going to pull out the smallest prime, which would be 2, and I'm going to be left with 3, which is another small prime, so I'm going to leave it there. With 40, I'm going to pull out 2, I'm going to be left with 20, I'm going to pull out another 2, I'm going to be left with 10, I'm going to pull out one more 2, and I'm going to be left with 5, which is a prime. So I'll have 2, 2, 2, and 5. So I'd want to find the LCM of this, so the highest power of each of these primes. So the highest power of 2 I see is 2 to the power of 3, because that's the highest power of 2 on one side. Highest power of 3 is just 3, because I only see 1 3. And highest power of 5 is just 1. Sorry, the highest power of 3 is 1, 2. But this would be our LCM. 2 to the power of 3 times 5 would be our LCM. But now we want to find the smallest possible positive value of k, which means that we have to turn this somehow into a square, and the smallest possible square. And the way we can do that, actually a small trick, is that we can actually increment the power of each of these primes, and we will get a perfect square. It's a small trick that you can learn. So instead of 2 to the power of 3, we're going to have 2 to the power of 4. We have then 2 to the 3 to the power of 2, and we have 5 to the power of 2. And when we multiply all this together, we'll actually get something that k would be equal to, if it's the smallest possible positive value of something that is divisible by 6 and 40. So 2 to the power of 4 is 16, 3 to the power of 2 is 9, and 5 to the power of 2 is 25. So if we multiply this all together, you can obviously do this on your calculator or just by hand, but I know the answer is 3,600. So that would be the way that we would find the smallest possible positive value of k if k is a perfect square. We would just increment all of these primes. And it's a tricky question. You could obviously do this more by trial and error. Once you get the LCM, you could start adding it out and multiplying it out and seeing when you end up with a prime. Not a prime, with a perfect square. But that's a little bit more messy, and this trick does work well. So if you ever encounter a problem like this, you can always keep it in mind. Okay, thank you for listening and have a wonderful day.